We just had South African load shedding, because of which the recording was interrupted. I'm not sure if I will be able to recover the recording of the first part of this lecture. In case I'm not able to do that, then let me say that we are discussing here the concept of duality, which we motivated from monoids and preorders, and then defined it for general categories. And now we were in the process of applying duality to prove a theorem that arises from the dual of a theorem we proved in the first lecture, that every split monomorphism is a monomorphism. The dual of that theorem says that every split epimorphism is an epimorphism, and we were investigating what split epimorphisms and epimorphisms are in the category of sets, and trying to prove that they're actually the same as surjective functions. So we were at the stage where we were considering a function f that's an epimorphism, which means that with every such diagram, this equality implies the other one, and we wanted to show that such f will be a surjective function. So we picked an element x in the codomain of the function, and then we defined w1 at every x prime to equal to some fixed element z in some set z. So we can just design a set, create a set z which has some fixed element z there. So that is when x prime is not equal to x. And we define w2 in the same way. And now the question is how to define w1 and w2 when x prime is equal to x. Any ideas there?
For w1, you could just map x to z. And then for w2, you could pick another point in z prime, and map x to z prime.
Right. So we basically need a set z with two elements. For example, this could be the empty set, and the set with the empty set is the only element. And then we define w1 and w2 this way. Now, the result of these definitions will be that if x is not in the image of f, right, then for such x primes that are not in the image, you see w1 and w2 are defined the same way. Then w1 composed with f will equal w2 composed with f. But then by the epimorphism property, also w1 and w2 will equal to each other. Which will give, of course, that which gives a contradiction, which gives that z equals z prime, right? So if we start with z and z prime being different from each other, it gives z equals z prime, because if w1 and w2 are equal, then they have to be defined the same way, also for x prime being equal to x. So if we start off with two different z's, z and z prime, then we can't have x not being in the image of f. And we cannot, of course, we can start with two different z's. We can just take a set with two elements and define w1 and w2 the way we have defined it, and hence force x to be actually in the image of f. So the assumption that x is not in the image of f leads to a contradiction. as explained below. Hence, X must be in the image of F, and this makes F surjective, because we were working with an arbitrary X, which is all we wanted to prove. The proof is then complete here, because we proved that every surjection is a split epimorphism. Every split epimorphism is an epimorphism by the dual theorem. And we also now prove that every epimorphism is a surjection. So that closes the cycle. So all the three concepts, epimorphism, split epimorphism, and surjection, these concepts are all the same. And this is a very interesting, it's a very interesting phenomenon, because this means that there are some properties of the category of sets whose duals are not true. So we spoke about the general concept of a category being invariant under duality, but when we pick a specific category, right, each specific category might have some features so that these same features are not shared by the dual category. What is such a feature? This feature, the feature that the monomorphisms and split monomorphisms differ for the category of sets, which we proved in the first lecture, because monomorphisms are just injective functions and split monomorphisms are injective functions, non-identity injective functions with non-empty domain. This feature, that they're different, is no longer true when we switch to the dual category, because when we switch to the dual category, we get split epimorphism and epimorphism, and they are the same thing. They're not different anymore. So individual categories may have some properties whose duals are no longer true for those categories. So in a sense, duality is only a powerful tool for getting free theorems as long as proving theorems in general categories is concerned. However, sometimes it happens so that certain specific categories have quite a lot of self-dual nature. In fact, even the category of sets has a lot of self-dual nature, and that's something that comes from my a recent research of mine, not so recent maybe, with my collaborators. But figuring out what part of set theory is invariant under duality can, or not just set theory, or any other concrete category, is a task of its own. And it's an interesting task, and it's one of the research directions in a way, which goes back to a paper by Saunders MacLean in 1950, where he started exhibiting duality phenomenon for groups. In fact, it is that paper in which he made a very powerful use of duality and stated that it's an important tool. It is the same paper where the notion of a product of two objects in a category was introduced for the first time. Remember, product is a special case of a limit. And I mention now products because this is where we want to, I want us to apply duality next. Let's take the notion of a product of two objects and let's dualize that. So we already stated that theorems can be dualized, right? Theorems can be dualized by just this table of translation, applying the table of translation. But of course, when you dualize theorems, you will have to dualize concepts as well, because some theorems are expressed in terms of concepts, and so the effect of dualizing theorems will give you as a consequence dualizing concepts, like we've done here. The concept of a split epimorphism is dual to the concept of split monomorphism. What does that mean? You write down the definition of a split monomorphism, you apply duality to that statement, so you translate the definition. So you basically consider this definition in the dual category, right? And then you translate back what it says in the original category, and then you've got a new concept. With epimorphisms, monomorphisms being dual concepts, and split monomorphism and split epimorphism being dual concepts, and so on. So what happens if we dualize the concept of a product of two objects? So let's recall what product is. So dualizing the concept of product. A product is defined in terms of a diagram like this, which has the property that for every other such diagram, for every C, and for any two arrows, F and G, there must exist a unique arrow here, H, such that the triangles commute, such that H composed with pi 1 equals F, and H, I meant to say pi 1 composed with H. Pi 1 composed with H equals F, and pi 2 composed with H equals G. Let's state this definition in the dual of a certain category C. In the dual category, an arrow runs from an object to X if it runs opposite way in the original category. So let's, like before, we state this in the dual of a category, and then we want to translate it back in the language of the original category. So we will still come up with a notation to put here. Let me put a question mark in the place of product for now. So we will have arrows going from X to that question mark. I will denote them by iota 1 and iota 2. And then the condition says that if I have another object C with two arrows, F and G, this time they're going into C, right? Because they must go opposite direction to F and G before. Then there must exist a unique H such that H composed with iota 1 is equal to F, and H composed with iota 2 equals G. So this is exactly the dual of these requirements, where, if you recall, for duality, we need to swap the order of composition. So we've swapped the order of composition. That's how from here we got that one. Okay, so we now have a new notion that allows to build some object out of two given objects, and we have this kind of arrows going into that new object, and we have the property that if we have arrows going to some other object C, then there is a unique way to transition from the object we're interested in to C, making these triangles commute, so that this composite equals that, and that composite equals that. To understand this new notion, let's use the category of sets once again. Let's try to compute what this will be in the category of sets. And if you remember, we kind of said to ourselves, I think it was last lecture when we were discussing limits, that the way we could have guessed that this is actually the Cartesian product of sets is by observing that this condition requires me for there to be as many arrows from C to X cross Y as there are from C to X times C to Y, because there is one unique H for each pair FG. So there is a Cartesian product happening there, right? So we wrote this out as, I mean, this becomes an exponential, one of the exponent rules for numbers. if I start counting the number of these arrows. So x to the power c, that's all the arrows from a c to x. Cartesian product with x to the power, with y to the power c is bijective. There's a one-to-one correspondence between pairs of f and g, and arrows h is bijective to x cross y to the power c. And if we didn't know what to put here, right, we could have guessed what to put here, because if I count the number of elements here when these sets are finite, this is the number of functions from c to x is the same as x to the power c, where x is the number of elements in x and c is the number of elements in c. And so x to the power c times y to the power c is equal to x times y to the power c. And then we just have to find a set whose number of elements is the same as the number of elements in x and y multiplied. And of course, that's the Cartesian product. So let's try to apply the same approach here to be able to guess what this question mark should be. So it says that the number of arrows from x to c, which will be c to the power x, times the number of arrows from y to c, which is c to the power y, if c and x and y respectively denote the number of their elements. This as a number should equal, or as a set that should be bijective to the arrows from question mark to c. What is question mark? Imagine these are numbers. What should go here so that c to the power x times c to the power y equals c to that power? Let me make the screen bigger while you are preparing to answer the question. What number is this? Surely that's not a difficult question. Or maybe that's why you're not answering, because it's an easy question.
I think it's a surprising expectation.
Sorry, could you please repeat that, Charles?
I said it's quite a surprising expectation.
What
you expect today is quite surprising.
So what shall we put here in the place of question mark?
If the numbers, we say x plus y.
Yes, we say x plus y for numbers. Now we need a set whose number of elements will be the sum of the number of elements of x and y. So if I have two sets, x and y, what is the set whose number of elements is the sum of the numbers of elements of x and y? And be careful, it's not union, right? Because if the two sets overlap, then the union will have less than the sum of the number of elements. Yes, Sasha?
The disjoint union.
That's right, yeah. Thank you very much. There are many ways to define disjoint union. One of them is to define it as x plus y equal x Cartesian product with 0, set with just 0 as its element, and union that with x Cartesian product with 1 as its element, only element, and as long as 0 and 1 are not the same element, you ensure that they're disjoint. You ensure that these two sets no longer have common elements because of the second coordinates being different. So this is quite a fascinating fact that the dual of the product turns out to be sum. This is something that we didn't know. There was no evidence of of there being any kind of any such relationship between multiplication and addition of numbers. We know that both of them are important. In fact, we first define addition, usually we first define addition of numbers, and then we define multiplication in terms of addition. But now category theory tells us that, in fact, the addition and multiplication, they're very symmetric to each other. And you can get one as a dual of the other. Of course, duality is an involutive transformation. So if I do duality twice, I revert back to the original thing, and that's something we didn't discuss yet. But it's very easy to notice this from our table here. What duality does, it reverses direction of arrows, right? But if you reverse it twice, you'll get back the same arrow. So it's worth noting that if I apply duality twice, I get back my original category. So the dual of a dual is the original thing back. And that's just because the same is true for each of these things. So already going back to monoids and preorders, this was so. If I swap the order of multiplication twice, then I'll get back to my original one. If I swap the direction of inequality twice, then I'll get back to my original one. In general, also in a category, if you take dual twice, you get back the original one. So that does mean that now product and sum are dual to each other, because dual of sum is product. Why? Because sum is itself dual of product, and doing dual twice gives us back. So dual of sum is product, and dual of product is sum. So from the lenses of category theory, a sum no longer has any advantage to product. When we introduce these operations from early on, right, in our lives, it appears as if sum is more important, because we first learn about sum and then we learn about multiplication. But now with this abstract approach of category theory, that importance is gone completely, and they occupy symmetric roles, and moreover they are actually dual to each other. There are many consequences of this surprising link between multiplication and addition. One of the simple consequences is the following. We could prove that in every category, X cross Y cross Z is isomorphic to X cross Y cross Z. Okay, what is an isomorphism? I don't think we've touched on the concept of isomorphism before, but if you think we have, and I'm forgetting it, please do let me know. I'm going to now quickly look at our previous notes just to make sure that we haven't. So, no, I don't think we have. That will be, I mean, that's a very important concept that certainly deserves its own lecture. But for now, we can just define it briefly as follows. An isomorphism is a morphism that is both a split monomorphism and a split epimorphism. So remember, a split monomorphism was defined as something having a section in one direction. So if you've got F, it was meant to be a split monomorphism when there is a G going back, such that G composed with F is identity of X. And a split epimorphism is opposite of that. So this swaps around. So the G that is required to exist still goes backwards. Let's call it G prime. But now we're requiring that F composed with G prime equals identity of Y. And so putting these two conditions together, we get that F has both kinds of inverses, this kind of inverse and that kind of inverse. It then turns out that in fact, the G and the G prime will equal each other. Why will it turn out so? So you can compose both sides by G prime here, both sides of this equality. That will give you identity of X composed with G prime, which is equal to G prime. But this one can be now composed in another order in this order, which will give us G composed with identity of Y, and so that is equal to G. So you see that G will end up being equal to G prime. So when something is both a split monomorphism and a split epimorphism, it in fact is such that this inverse from both conditions match with each other, and that's what isomorphism is. And we already know that split monomorphism is dual condition to split epimorphism. But if we're requiring both of them to be true, then this notion of an isomorphism surely must be self-dual. What do I mean by that? So you take an isomorphism in the dual category. In the original category, it translates to 1. So in the dual category, it's something that's split monomorphism and split epimorphism. In the original category, it will be the dual of each part, right? In other words, split epimorphism and split monomorphism. But that's just rearranging the order, so it's still an isomorphism. So an important theorem here is that which we kind of proved now just by talking about it, isomorphisms in the dual category are the same as in the original category. So we then say that the concept of an isomorphism is self-dual when this happens. So when a concept is invariant under duality this way, it's said to be self-dual. Remember, the definition of a category itself is invariant under duality. So already a category is self-dual, and some of the things defined inside a category will also be self-dual, like the concept of an isomorphism. Now, going back here, this notation simply means that there exists an isomorphism from here to there. And it will be possible to prove that this is true in any category, just by using the definition of product. Let's dualize this theorem. Apply this theorem in the dual category. The dual theorem will say that this is true in the dual category of any category. And now let's translate it back what it means in the language of the original category. Multiplication in the dual category, in the language of the original category, is addition. It's something called co-product, or just a sum. So we will get that x plus y plus z, and remember, there being an isomorphism will be a self-dual property because isomorphisms are self-dual, right? So being an isomorphism in the dual category is the same as being an isomorphism in the original one. So we'll get that this is isomorphic to that. So then category theory tells us that if you know that, if you already have proved that multiplication is associative, you don't need to prove that addition is associative separately. It's just an application of the dual of the other result. And conversely, we could have started with this, prove that, and get the other one as a consequence. So the fact that multiplication and addition are dual to each other is not just some fascinating fact. It actually has use, and the use of it is that everything I will ever prove about multiplication will now give me a theorem about addition, and conversely. And one such thing is very basic thing, the associativity of multiplication. we don't have only duals for products, we have duals for arbitrary limits as well. So dual of the concept of limit is a name of its own. Duals of limits are called colimits. So in this little portion of the lecture, I tried to link up the concept of duality with limits. We will have definitely a separate session to go deeper into colimits. We just looked at a very specific colimit here, the sum. But what I want to do in the time that still remains is to link up duality also with another lecture of ours, and that was the one we gave just before the previous one. So the previous lecture was on limits, and the one before was on adjunctions. So I would like to show you how duality links up nicely with adjunctions. That will be in the form of a theorem which we are not going to prove, because essentially the theorem is almost like going to prove itself, because it's it will be just a matter of translation and the application of duality. So the theorem says that for every adjunction, so remember, a junction consists of two categories, C, D, and then a pair of functors, F and G, and natural transformations. And what I'm going to do now is to take the duals of C and D. I'm taking the duals of both categories. Remember, functors are defined by mapping objects and arrows. In a dual category, the objects and arrows themselves don't change. Their direction changes, but the objects themselves and the arrows themselves don't change. The sets are the same. So the same object function and the same morphism function that defines my functor from C to D, let's say, will define a functor from C op to D op. And it will actually be the same functor in the sense that it will be given by the same object function and the same morphism function. So when we switch to dual categories C op and D op, F will still be a functor from C op to D op, and G will still be a functor from C op to D op. But now I'm going to put them in a different order. I will first put G here and then put F. And I'm also going to swap it out around the order of natural transformations. And the theorem says that this is still an adjunction. The crux of the matter here in the definition of adjunction is two equations, right? We are requiring that, I'm just recalling from our last our lecture on adjunctions, that we're requiring that this arrow composed with f of eta c must equal identity of f of c, and g of epsilon d composed with eta g of d must equal to identity of g of d. Now let's try to dualize these to get convinced that we get same equations, but with the order of the transformations and the functors swapped around. Dualizing this means what? Nothing to dualize here, because the object function didn't change. Identity arrows don't change, so that stays the same. Even the transformations don't change. They stay the same, except that they're going opposite way now. They are the same arrow, but they go opposite way. So previously, eta c was going from C to gf of C. But now in the dual case, if I take this eta c and I consider it in the dual category, it will run from gf of C back to C. So this is in C up. This is what happens in C up. But remember, this was exactly the direction of epsilon. Epsilon was going back from the composite of functors to the object. So epsilon previously was going from fg of an object D to D. And if I reverse the direction of the arrow here, we will get a direction which matches with the intentional direction of eta, right? So it will go from D to the composite in the dual category. So that's all that changes, the direction. And then, of course, also the order of composition should change, right? So the dual laws will be F eta C composed with epsilon FC equals identity FC, and eta GD composed with G of epsilon D equals identity of GD. So we get some new concept, right? It seems to be a new concept. So now the functors run between the categories C op and D op. We've got these transformations in C op, and the other one actually is not in C op, but it's in D op, right? The other arrow. I'm kind of skipping over the detail that there will still be natural transformations. If you take the naturality square and you reverse the arrows there, you still get naturality square. Just believe me on that for now, because maybe I can explain it after finishing this, so that we don't make too much mess here. And then the most significant part, these equations, they transform into these. But now I can see that this is kind of similar to the first one here is kind of similar to the second one here, except that now the role of epsilon has been, the role of eta has now been taken by by epsilon, and the other way around, the role of epsilon has been taken by eta, which matches with what we remarked here, that eta in the dual situation obtained the role of the direction of the epsilon. And the same for the second one here. The second one there matches with the first one. So basically, we get the same conditions. We get an adjunction. So let's conclude this discussion by drawing a picture showing that dual of a natural transformation will still be a natural transformation. So that will apply to arbitrary two categories, let's say X and Y. So if I have two functors, let's say F1 and F2, and I have a natural transformation n between them, what does that mean? For every object X, I have an arrow from F1 of X to F2 of X. And I also have a condition that tells me that if I have an arrow from X1 to X2, an arrow F, then I'm going to have this F1 of X1 going down to F1 of X2, which is F1 of the F arrow. And then here I have the natural transformation component at X, n, at X1 rather, going to F2 of X1. Here we have n going to F2 of X2, and here we have F2 of F. Recall that a natural transformation was a family of arrows like this, such that these two composites here are equal. In other words, the square commutes. Now, what will happen if I'm considering dual categories? So I go from X to X op now. I want to interpret this in the language of X op. We agreed that F1 and F2 will stay F1 and F2 because they're just determined by object and morphism functions, and these sets haven't changed. Only the direction of arrows has changed, but not the sets of objects and morphisms themselves. Although sometimes people prefer to call this F-op, just to distinguish this F1 from that F1 in the sense that the domains and codomains have changed now, although the mapping is still the same. But let's stick out to our grid notation for now. The direction of n will change, but n itself won't, because what was n before? It was a family of arrows, right? It was a family of certain arrows. I'm going to keep the same family. I'm going to still keep the family nx. But because the direction of arrows has changed in y, now my family will be going from f2 of x to f1 of x. It's still the same family, except that each member of that family has now opposite direction in the dual category to the direction it had in the original one. And what becomes of this diagram? Well, the direction of arrows need to change, and then composition also swaps around, right? So we just draw the new picture with new directions. So f now goes from x2 to x1 because we dualized x as well. And for every such thing, I now require the following diagram to commute. Sorry, the direction should have changed there. So this is nx2, this is nx1. But you see, this diagram is the same as this one. It's not literally the same, but remember we were requiring this for every f. This is exactly to say that n is a natural transformation from this functor to that functor. Because if you just rotate this diagram by 180 degrees, right, matches exactly with this one. This is the same naturality square, the same condition of being a natural transformation. This time between functors f1 and f2. So the notion of natural transformation is invariant under duality as well, as long as we're taking duals of both the domain and the codomain of the functors. Except that direction has changed. The direction changes, but the condition that doesn't. And so that's why coming back here, I mean, that helps with the previous theorem because we did want these new things to be still natural transformations. Now we know they are. And what makes them into an adjunction are these equations, which translate to these. But that's exactly the equations with the roles swapped around, with the roles of eta and epsilon swapped around. So you start with an adjunction, you take the dual categories, you still get an adjunction, except that now what before was left adjoint, f here was left adjoint, now it becomes right adjoint. And what before was a right adjoint, it now becomes a left adjoint. And what before was a unit of adjunction, it now becomes a co-unit of adjunction. And what before was a co-unit of adjunction, it now becomes a unit of adjunction. So things swap around. This is a very important fact as well, because in the previous lecture, when we defined limits, we said that the right adjoint always preserves them. The right adjoint in an adjunction always preserves limits. Dualizing this theorem, we will get that, remember what happens to the right adjoint? The right adjoint becomes the left adjoint in the dual adjunction, and the limits turn into colimits. So now we know that left adjoint always preserves colimits. It's just one example of how duality still continues to work here in terms of producing new theorems out of the old ones. Okay, so the purpose of this lecture was to introduce you to the idea of duality. Of course, we only skimmed the surface. There's much more to be said here about duality, and we will be saying many more things about duality in future lectures. but I think that for now we've done a relatively good exposition of duality, trying to link it up with the other things we've been discussing so far in the course. Would anyone like to ask any questions or make any comments in the recorded session?